Okay, let's take a look at question number 38. Regina filled 4 metal cans with 200 ml of water, right? And they're all metal cans, you can see. Now, and they are all 80 degrees Celsius. So at the start of the experiment, they are all 80 degrees Celsius, so it's quite hot. Now, she then covered covered the 4 cans with material A, B, C, and D, and she placed also a thermometer there to measure the temperature. So after that, she placed the 4 cans under the sun for about 25 minutes, okay? And recorded the temperature of the water after the 25 minutes. So material A, it starts with 80, and then at the end of 25 minutes, it becomes 60.5. So there's a drop in the temperature, meaning to say it actually loses heat. Yeah? Next, B, 80 degrees then becomes 73.5. So again, it loses heat, but in this case, it loses heat as compared to A, it loses heat at a slower rate. That's why it's 73.5 degrees, right? Now, then C is 58. This one, it loses it at a very, very fast rate, and D, 80 to 67.5. So if you take a look at this, I'm comparing this four. Now, B means that B lose heat at a slower rate. Or I can actually say, because I'm comparing 4, is the slowest, lose heat at the slowest rate. Whereas for 58, see from 80 go all the way to 58 just by 25 minutes, it's able to lose heat at the fastest rate. Sorry, this one should be the lose heat at the slowest rate, and this one's able to lose heat at the fastest rate. Okay, now, so of course, by looking at all of this, we all know the topic now is definitely your P4 heat, right? And the key concept here that we are looking out for when you talk about heat is something about losing heat, gaining heat, right? At either a fast or slow rate. Now, let's take a look at the question then. Based on the data above, which material A, B, C, D is most suitable? So I see, again, what am I doing? Which material? A, B, C, or D? I'm asking you to compare. So, but right now I'm not comparing between two, I'm comparing 4 items. So, in this case, it is a comparison question. And not only that, I'm comparing 4 items. So I do not need to put the comparative adjective, but instead I put a superlative adjective. What does it mean by superlative adjective? Okay, your comparative means more, faster, all the and all the more, right? Superlative in English, we say that it is most, least, fastest, slowest, okay, or the us or the most or the least. Yeah. So which one is the most suitable to make an insulated bag, okay, that keeps food frozen for the longest possible period of time? So it's just like when you want to buy your ice cream, right? You don't want it to melt. You want to keep it in an insulated bag to keep it frozen. So what does it mean? You want to gain heat or lose heat at a slower rate? Yeah, you want it to lose, you don't want it to gain heat faster, right? So you want it to gain heat at a very slow rate, because right now you want to keep the food frozen. And what is the one that makes food frozen to melt? Like for example, you take an ice block, right, which is frozen, you put it outside, take it out from the freezer, you put it outside. How does it become water? It will gain heat, am I right? So here you need to answer the question. Some of you just say, oh, material B and it lose heat at the slowest rate. No, I need you to talk in context of this question here, talking about gaining heat. It gains heat. Okay, so in this case, you can just write a note for yourself. If I want to keep my food frozen for a long time, it means that I need to, that means the food needs to gain heat at a slower, slowest, right? Because now, right now I say it's the superlative, at the slowest rate. It needs to gain heat at a slowest rate. So something that gains heat at the slowest rate, gain or lose heat at the slowest rate, which one is it? Is it so? Is it A, B, C, or D? Definitely it's not A and D, right? So it's between B and C. Now, B, it lose heat at a slower rate. When something lose heat at a slower rate, it also gain heat at a slower rate. That also means the same way. So, okay, so when something lose heat, it also gains heat at a slowest rate. When something lose heat at fast rate, it also gains heat at a fast rate. And of course, here we can also talk about a conductor and insulator. Am I right? So a good conductor of heat is something that lose and gains heat at a faster rate. So this one is a good conductor. This one is a poor conductor. But right now, I'm not asking you about whether it's conductor or not. Right now, I'm just asking you which material, right? So in this case, which one? Of course, we are talking about material B. Then, a lot of you didn't explain. You need to explain in terms of the question. So, how is it that I need to keep my food frozen for a longest time? You choose material B so that it will allow the food to gain heat at a at the slowest rate. It allows food to gain heat at the slowest rate. Okay, so that is something. That's why I choose material B because it doesn't. But I mean, there's still gaining of heat, but it gains heat at a slow rate, the slowest rate as compared to the other three. Okay, so of course, when you put slowest, you need to already say as compared to A, C, and D. Okay, because you are already doing the comparison here by using the word slowest. Clear? Okay, so this is the main idea in this question here. Okay, now let's take a look at the part B. Regina repeated the experiment. Right now, the metal can is wrapped in material A and a plastic wrapped in and a plastic, sorry, a material A and plastic and can wrapped in as shown below. So a plastic can wrapped in material A, sorry, a plastic can wrapped in material A, and the other one is the same one, metal can wrapped in material A. So the only difference is this is a plastic can and this is a metal can. Now, just by looking at this, you can straight away tell me, hey, they are comparing whether between plastic and metal. So plastic is a what kind of material? It's a good, sorry, it is a poor conductor of heat. Straight away, you can tell me that, right? Plastic is a poor conductor of heat. Now, and then how about metal? So, sorry, a poor conductor of heat would mean that it lose or gain heat at a slower rate. Whereas metal is a good conductor of heat. So it actually lose or gain heat at a faster rate. Okay, so that is the key concept that we are testing you here in this question. Alright, now let's take a look then. She recorded the temperatures of the water after 25 minutes. So metal can 80 then becomes 62.5 again after 25 minutes. Plastic can 80. Oh, they ask you to predict. Right now they don't know, they didn't give you the temperature, but they ask you to predict or make a good guess of what will be the temperature of the temperature of the plastic can will be higher, lower, or the same. Whether it will be higher, let me highlight, lower, or even the same. Now, think about it. You already told me here that plastic is a poor conductor of heat. It loses and gains heat at a slow rate. Metal, however, is a good conductor. It gains and loses heat at a faster rate. So it means here that my plastic can here will lose heat at a slower rate. It means I'm not losing much heat, so my temperature will it be higher, lower, or the same? Definitely higher. Okay, so that is definitely higher. And you can just stop there because right now they ask you to explain why is it higher. So again, using your key concept that you have already written here. So what about plastic? Okay, of course you need to refer back to the question. Plastic is a poor. Now, oh sorry, I missed out a very important point here. I'm comparing plastic and metal. Can you see? Why is whether plastic is higher, lower, or the same? See, I'm again higher, lower. So all these are comparing. I'm comparing the plastic to the metal. So I need to have a comparative adjective. Okay. So in this case, plastic is a poor conductor. Can I say that? Can I say that plastic is a poor conductor of heat? Can I say that? Definitely not, because I am not comparing to the metal. So some of you can say plastic is a poor conductor of heat, but not metal, or as compared to metal. But if without even putting metal, you can say plastic is a poorer. Okay, you see, remember Miss said every time we talk about comparative adjective, you need to have the er. Okay, so those of you who just say plastic is a poor conductor of heat, 0 marks because you are not comparing. So plastic is a poorer conductor of heat, and this will give you half a mark. Now, where does the other half a mark come from? You need to explain what is this poorer conductor of heat. This is just your evidence. What is your concept of poorer conductor of heat? This means that the plastic, again, I'm referring to the plastic. I'm not saying poorer conductor, any material of poorer conductor of heat. This means that the plastic, now, loses heat. Okay, so because in this experiment we are talking about losing heat, right? Loses heat at a slower rate. Now, see, then again I am using the word slower. Again, it is a comparative word. So if you tell me it means that plastic lose heat at a slow rate, this will be 0 marks again. Okay, so this one will give you another half marks. So that is 1 mark for you. Okay. Okay, if you realize, I actually skipped question number 39 because I would want to go through that in class because there's a lot of drawings that I need to show you, okay? So I can draw the circuit test. I can show you by drawing, and it's quite difficult using a computer, yeah? So, okay, let's take a look at question 40. Since you wanted to find out how objects A, B, C, D, so different objects made of different materials, okay, react with a magnet on a retort stand. So this is a magnet that is clamped by a retort stand. That means this retort stand is holding this magnet here, okay? And he set up the experiment below by placing an object. So that means I place this object, I scotch tape it, okay, to this cardboard here. And this cardboard here is attached to the spring. So imagine if I have the spring that's attached to the cardboard and my object is attached to my cardboard. So if this object here is being pulled, the cardboard will also be pulled up and this spring will also be pulled up. It means that the length of the spring would increase. However, if my object here is being something, there's a force here that is pushing my object A down, cardboard will also go down, my length of spring will also decrease. It will also go down. Okay, so of course here you can then tell me the topic is Petri magnet. Now, then you need to tell me what is the one that's causing it to go up here. So an object here that is going towards a magnet, the interaction is it attracting or repelling? Is going towards a magnet. Attracting, right? So it is attraction. So attraction here can be magnetic materials are attracted. Magnetic materials are attracted to magnets. Oops, sorry. Spelling. Magnets. Okay, attracted Okay, magnetic materials are attracted to magnet. Another way of attraction is, this is number one. Of course, we say that magnetic materials attracted to magnet. So magnetic materials are your Superman is not cruel, steel, iron, cobalt, and nickel. And number two is unlike pole of magnets attracts, right? However, in this case here, okay, so let's not talk about that. Okay, let me skip that for a while. Okay, then something that pushes it down. Okay, imagine if I have an object here and there's a force that pushes it down, and this force here is coming from where? It's definitely coming from magnet. And so, what is the force that is pushing when it comes from a magnet? It is called repulsion, right? So there's attraction and there's also repulsion. Repulsion can only occur when, all of you know, repulsion occurs with the magnets, right? Only magnets can repel each other when their like poles. Dear. Okay, wait. Let me go back. I don't know why. Just now we say that the option 2 is magnet unlike poles of magnet. Let me just write it down. I don't know what's it goes off. Okay. Again it goes off. Sorry. It is like that. Okay. I think I better not do that anymore. Okay, so repulsion, it occurs between magnets, right? When their like poles are facing each other. Okay, so now let's take a look here. Object A, 6 cm. Okay, that's the original length of the spring. And then when I put object A, the new length of spring is 4. So there's a pushing force, something that is pushing it down. So something that is pushing it down, we all know it is repelled. It's getting repelled. Now, then I put object B, and there is no change in the length of the spring. That means nothing is happening here. This is the original length of spring, right? So nothing happened. Nothing happened. When nothing is happening, that means what can a material be? Is it a magnet? Definitely not. Is it a magnetic material? No, because a magnetic material is attracted to it. So nothing happened would mean that it can be a non-magnetic material. Okay? Now, and then 6. Oh, then when I put object C, it became from 6 to 9. So that means something is pulling it up. It's attracting. Then you say, oh, but Miss Lana told me, oh, magnetic material. So it can be a magnetic material. Now, some of you say, hey, but it can also be a magnet. What? Because magnet, like Miss Lana say, right? Unlike poles of magnet attract, right? Yes, but you cannot confirm that. How can you confirm that? Because you must turn this object to the other side to see whether it is still attracting. So you cannot confirm whether it is a magnet because you don't see any repulsion. You only see attraction first. Okay, so maybe we just put magnetic material. You cannot confirm that. And then object D, again, is something like object A. From 6 cm, it now becomes 3 cm. So something is pushing it down. Again, it is repelled. So based on the above results, which object A, B, C, D is a magnet? So confirm a magnet. Which one? And give a reason. Okay, let me delete this. Give a reason. Now, so of course we talk about those that repels is confirmed a magnet. So in this case, the one that repels is object A and D. Now, then you need to explain, right? So first, tell me what you observe, okay? So what is what that is. Also, remember your choice, then your explain and your reason, evidence and reasoning. What is your evidence here? That means what do you see here for A and D? So you can say the spring was compressed. Okay, maybe you don't know how to say the spring is compressed. You can also say the length of the spring decrease. So you first tell me what you observe. Okay, that's how you refer back to the question. This one will give you half mark because you are stating an observation. What is your evidence? Your evidence is the length of this A and D. Can you see it decreases? Okay, then you have to explain, right? Why do you think it decreased? This means that object A and D repel. Now you are telling me a concept. Can you see? This is evidence, this is concept, is being repelled by the magnet. This will give you another half mark. Now, you cannot stop there because, so what if it's repelled by the magnet? Okay, then of course you can say this means that object A is being repelled by a magnet. Actually, I would this question is quite good enough. They give you half mark for this one, but you need to actually tell me that only this is the key concept. Magnet repel magnets when like poles are facing each other. This is the key concept. Now, can you see that I'm putting in the key concept together by making the reference to the question and just explaining the key concept together in the context of the question. This will give you the full marks. Are we all clear? Okay. Okay, now the second part of the question. See, you then use a magnet. Okay, can you see the diagram here? Use a magnet and one of the objects mentioned above, that means mentioned just now, to make the magnetic door stopper as shown below. Now, the magnet was secured to a holder. So there's a holder here, okay, attached to a wall. This is the wall, this is a holder, this is the magnet, yeah? And then it's placed at part Y. What? Sorry. While the object was placed at part Y. So I have another object. It's placed at part Y attached to the door. Now, the magnetic door stopper can help to hold the door open. Okay, this is like your house. You want to keep the door open and not let the wind blow it, and then your doors will get slammed, right? So you have a magnetic door stopper, yeah? So you know that the magnet here is here. And this is the knob, and of course it's attracting here. So based on the above table, okay, you have to refer back to your paper based on the table because I can't show you that here. Which object A, B, C, D was suitable for placing part Y as the magnetic door stopper? Now, this is easy, right? Because I'm just asking something that is attracting. This is attracting together. Okay, so definitely I need something that attracts. So if you refer to the table, okay, something that attracts is definitely not A and D because it's repelling. It's definitely not B because nothing happened. And it is only C because it's attracting. And how do you know if it's attracting? The length of the spring is increased, right? The length of the spring is increased. So, which object should you choose then? Based on the object, which is the most suitable? See, again, I am comparing, and now I'm comparing between four objects. So, here, comparison, and it is a superlative adjective that you are supposed to use. Okay, now to make a door stopper, and I need to give a reason. Yeah. So always don't forget. So it's similar like the question just now, only that now I'm asking you for something that attracts. Okay, so of course you say first, your choice is object C. Now, why is it object C? Again, what is your evidence that object C attracts? Okay, so you must say the length of the spring increased. This will give you half mark because you are observing that the length of the spring increased. Now, then tell me, what does it mean when the length of the spring increase? Meaning object C was attracted to the magnet. Okay, don't use the word like an object C go to the magnet or something like that. Use the right terms, attract, right? In magnet, we always talk about attraction. So it means that object C was attracted to the magnet, and that will give you another half marks. Okay, so if you can see here, this is the actual 1 mark. So you just have to tell me what's your observation. The length of the spring increased, and why is it increased? Because object C is attracted to the magnet. Okay, you can't just say, oh, there's attraction. What is attraction? What is attracted to what? So object C is attracted to the magnet. Of course, you can also say that right here they don't ask you what's the material. So you can say it is a magnetic material or something like that. Yeah. So if they ask you what is it, then you can say either iron, steel, cobalt, or nickel. But in this case, this question here, they didn't ask that kind of question. Okay. Okay, let's take a look at question 41. Jungwei placed some food on the barbecue grill. So it's a barbecue grill as shown below. This is like your barbecue grill that you see during your picnics or anything like that. Okay. Now, and then she put a chicken fillet there and sausages definitely. So after that, he noticed this black grill line on the sausages. I'm sure you all have seen this, right? When you go to barbecue session and you see, hey, how come there's black things on your sausage? So this is a black grill line. Now, so what's the question here? Based on the observation, why were there black grill lines? So I want you to explain why. Explain why there is only black grill lines on only some parts of the sausage. Some parts only, not all parts of the sausage, right? Why is there a black grill line on some parts of the sausage only? Now think, look at this thing, it is a metal grill. Then after that, there's black line here. There's something got to do, and I'm heating it up. Definitely, this when you talk about topic, you definitely know it's something about your heat, right? And something about metal. They even tell you here that it's a metal grill. So metal, metal is what kind of thing? Metal is then you can say, oh, maybe they're talking about the material, whether it is a good conductor or whether it's a poor conductor of heat. And you know that metal is a good conductor of heat. So yeah, conductor of heat, right? And then now ask yourself here, how does this, or when you go to barbecue sessions, how do you actually cook this sausage? Is it that must it always be in contact? That means all the parts of the sausage must be part of contact with the metal grill, so it's a good conductor of heat. No, right? So what happened? You put charcoals at the bottom, right? And you heat up the you heat it up. Okay, the charcoal becomes very very hot, and you can see all this, the air, right? The hot air is the one that will heat this sausage up. So that is the way how you actually cook, right? So it is via the hot air, the heat that is being produced by the charcoal, the air itself, yeah? So right now there's two ways here. There's a hot air that's coming out from these holes here, and there's also this metal grill lines here. Okay, now, so something about air, let me write here. Something about air, the hot air, the heat, and the metal grill lines. Now, okay, we do this question one by one. This is a very tricky question. Why is there black grill lines on the sausage? First, you tell me, where is this? What is this black grill line? Definitely, it is the what? This metal grill thing, right? See, can you see the black grill lines will form on the sausage, right? It's actually by the metal grill. So, you can say that the surfaces of the sausage with the black grill lines. So you can say that this sausage with this black grill line, or no need to say surfaces, you say the sausage with the black grill lines is due to the fact that it is in contact with the metal grill. Okay, and this will give you half a mark. This is understood, right? Because you just state what's your observation. That means what's your evidence. You see this metal, this black lines, these are your, because this sausage is, you are placing this sausage on the metal green line. So as long as you can tell me this sausage is on the metal green line, and these lines, these black lines here is actually because it's in contact or is placed on the metal grill, I will give you half mark. Okay, now, but why is it dark black as compared to the other parts of the sausage which is just exposed to the hot air? Now, think about in terms of good conductor of heat. Metal, all of you say it is a good conductor of heat, right? How about air? Because this is something that most students don't think about. Okay, air, is it a good or a poor conductor of heat? Air is a poor conductor of heat. As compared to other things, air is usually a poor conductor of heat. Okay, so can you just take note there and write it? Air is actually a poor conductor of heat. Okay, so now we talk about good conductor of heat. I'm not going to write it here again, but good conductor of heat is something that lose or gain heat at a very fast rate, and poor conductor of heat means it lose or gain heat at a slower rate. Now, right now we are comparing the parts of a sausage that's in contact with the metal lines. Is a good conductor of heat. Definitely, it will cook faster, right? Because it is gaining more. It is gaining heat at a faster rate. Okay, but air, those surfaces that is exposed just by the air, the hot air, because air is a poor conductor of heat, it gains heat at a slower rate. So that's why it's not burnt. Okay, so that is actually the reasoning that you are supposed to give me here. But how now do you put it into sentence? Now, if you take a look here, I'm comparing this part, black part here, to the other normal parts of the sausage. I am again comparing, because I say, why are there only black green lines on some parts of a sausage? Comparing again. So I need to have a comparative adjective. Again, I don't see in some of your answers. I keep on emphasizing on the word comparison. Right? You cannot just tell me metal is a good conductor of heat. You need to tell me metal, remember, metal is a better conductor of heat as compared to air. That's something that you have to tell me. Okay, so you can say metal reel is a better conductor of heat. Metal is a better conductor of heat. Wait. Okay, metal is a better conductor of heat than air. Okay, so you need to tell me this. Is a better conductor of heat, and this will give you the half a mark. Is better conductor of heat than who? Than air, because you are comparing. Okay, so with that, this is not yet. So so if it's a better conductor of heat than air, what will happen? So again, insert your key concept now. What will happen if it's a better conductor of heat? So the parts touching the metal reel will gain heat faster. Can you see? And cooked faster. Full stop. So again, I'm using the comparative word here, gain heat faster, cook faster. Now, because why didn't I just say, oh, a good conductor of heat gain heat faster? I'm again saying the parts touching the metal grill. So I'm referring back to the question. Remember, you cannot just add your key concept to a question, because that will just mean that you are just vomiting the key concept. You need to explain it in according to your question. So you marry the question together with the key concept. That's why I say the parts touching the metal grill gain heat faster. So instead of just saying good conductor of heat gain heat faster. So tell me the sausage that is touching the metal grill gain heat faster and cook faster. Clear? That is part 1. Okay, now let's take a look at the second part. Junwei then placed an identical sausage, identical sausage A on a metal plate. Now, can you see now the metal plate? The sausage is touching everything, every part of the metal plate, right? It's not just the metal grill just now, there's some spaces, right? Now, so the metal plate was placed over the same amount of heat used in barbecuing the grill. So it's the same heat, everything is the same, only that the metal plate now, the whole sausage, the surface of sausage is touching the metal plate. Just not only the metal grill, right? It's touching parts of the sausage. Now, will sausage A be cooked faster than the sausage placed on a metal grill? So again, I am comparing. Will it cook faster? Now, here, look at it. What are they? See, the thing about science is, right, what gives you a clue to the answers itself is for you to look at the differences between the setups. For example, look at this setup here. The whole sausage is touching the metal plate. Just now, the sausage is touching only parts of the metal plate, which is the grill, right? So something about the space. So in this case, we are definitely talking about something about touching the surface contact, etc. This is what we call the surface area. So we are definitely talking about the surface area or a greater surface area of a sausage that is in contact to the conductor of heat. Okay, and now, so we have to give a reason. So would it be cooked faster? A lot of you can answer me this. Yeah, definitely, right? Yes, it will be cooked faster, but now I need to give a reason. So something about the surface area, and we are comparing. So the metal plate here has what? Greater surface area. We have to add the word greater. So we can say that sausage A has a greater surface area touching the metal plate, or you can either say vice versa. The metal plate has a greater surface area touching the whole sausage. So what I'm trying to see here is that there is a greater surface, the whole sausage, I mean the whole surface of the sausage is touching the metal plate. That is the key idea here. Okay, so I'm using surface area to explain in scientific terms. So the sausage A, greater surface area of sausage A is touching the metal plate. Now, this again is just your evidence. Remember your choice, evidence, and reasoning concept. Sorry. So again, touch it. So this is your evidence. Oh, sausage A has a greater surface area touching the metal plate. Now, what is your concept then? When it says is touching it, touching the metal plate, the whole surface area touching. So it means that it can gain what more again comparative heat, or you can say instead of saying that, you can also say I put an or it, so that it can gain heat faster. So cook faster, gain heat faster, and cook faster. Full stop. So that is it. Okay, you just need to give your evidence, greater surface area, and when greater surface area definitely is cooked faster. Why? Because it's gaining heat faster, or you can say it can gain more heat. That's all. Yeah. Okay, 42. Roxane placed two similar empty glass bottles. So it's the same glass bottle A, glass bottle B, but now she put it in two rooms, X and room Y, and these two rooms have different temperatures. Can you see here? So for example, maybe one is aircon, one is not aircon, one's not aircon. Okay. Now, so it's not being told what's the temperature. So after 2 hours, she removed the two glass bottle from these two rooms and placed them at the same temperature, same room of temperature 27 degrees. Now, 15 minutes later, she observed water droplets forming on the outer surface. Okay, this is important. Water droplet forming on the outer surface of bottle glass A, but there is no water droplets on bottle B. Now, before you even answer the question, again, identify what is your topic. Now, your topic, something about, hey, there's water droplets on the surface. I mean, whenever we talk about water droplets, we're always talking about the P5 water cycle, right? Okay, so we're talking about the P5 water cycle. In this case, why is there water droplets being formed? You need to know, this is the key concept here that is being tested. Why is there water droplets formed? Water droplets, when forming on the surface of the on your glass or even on any other things, is when there is condensation taking place. So that is the key concept. And how does condensation taking place? Remember, take place. I remember I always tell you, in condensation, in any processes of water cycle, you need to have three things, right? Number one, condensation, is it losing heat or gaining heat? It's a process of losing heat. Then the process is condensation. Then what is the change of state? Water, vapor to water droplets. That is the key main point here. So it needs to lose heat, right? So now that is the key concept. Okay, let's take a look. So why is there no water droplets? That is the question on the water B, on the outer surface of water B. Okay, wait a minute now. Before you answer this question, I want you to analyze this question first. Now, I put these two bottles in different room. Okay. Now, when imagine right now, I want you to imagine you put your bottle in the freezer. Okay. You take out that bottle and put it outside. Now, what do you see after some time? You will see water droplets form on the outer surface of the glass bottle, right? Why is it so? Because in the freezer, it's very, very cold, right? So your surface of your glass bottle will be very cold. Your surface of your glass bottle will be very cold. Now you put it outside. The outside temperature now is very hot, right? About 27 degrees or room temperature 27 degrees. So what will happen? The bottle, the glass bottle that is the cold glass bottle, so the hot air, the hot surrounding air, what will happen to it? Remember we talk about condensation, we always say that it touches a cooler surface. Okay, so whenever we talk about condensation, we always say that it touches the cooler surface. So you must know what is the cooler surface here. In this case, the cooler surface is the glass bottle A because it's from a cool place. For example, so the hot surrounding temperature, the hot surrounding air touches the cooler surface of this bottle, loses the heat, and then form the water droplets because it changes from water vapor to become your water droplets. Okay, so that is the key idea here because so you know then glass bottle A is very, very cold. The surface of glass bottle A, so you can put here surface of glass bottle A. Oh yeah, I cannot see. Is cold. But now there is no water droplets forming on glass bottle B. There can be many reasons, you know. And what is this? A few of these reasons then? Okay, let me just write it here. Glass B. Why is it that there's no water droplets form? Meaning it is not a cool surface, right? So it means the room temperature is 27, right? Obviously this bottle here that has water droplets, it is lower. The temperature is lower than 27. That's why it's cooler, right? That's why there is water droplets. But in this case, this glass bottle B, it can be, yeah, it can be that number one, it can be the same temperature. Now, a lot of you tell me that, oh, glass bottle B was put in in room Y, which is the same temperature as 27 degrees Celsius. I'm not asking you about the room. I'm talking about the bottle. So the glass, the surface of glass bottle B, the temperature of the surface of the glass bottle B is maybe temperature. Let me just write short form. Temperature of the surface of glass bottle B, it can be is the same as 27 degrees Celsius. Some of you put uh, same as room temperature. Here, can you not write room temperature because sometimes room temperature is subjective. You use back 27 degrees is what is given to you. So you use 27 degrees. Or it can also be, if it's not the same, it can also be hotter, right? It is even, or you can say the temperature is higher than 27 degrees Celsius. It cannot be colder than, it cannot be lower than 27 because then it means it's cold. So it's either the same or it's higher. Okay, so that is the reason why there's no water droplets. Now, so a lot of you explain in terms of glass bottle A. Again, I'm asking you what is the glass bottle B. So you must explain it in terms of glass bottle B. So there can be many reasoning here. I'm just going to give you one reason. Okay, so you can first say that the outer surface, see, I'm very specific. I don't just say surface because surface can be inner surface or outer surface. So you say outer surface of glass bottle B was not full enough. So I can say that it's not full enough, or I can also say, let me just write out, or I can also say that it has the same temperature as 27 degrees Celsius. Okay, or I can even say has a temperature higher than 27 degrees Celsius. You write that down. So this will give you the half mark because you just tell me that the surface here is either the same, not cool enough, or the same temperature as 27, or even a temperature higher than 27. Now, then what happened? So, now, what happened if it's the same or higher, or not so cool enough? Water vapor in the surroundings cannot lose heat. Cannot lose heat, right? So that is the main point. It cannot lose heat and cannot condense into water droplets. That's all. Okay? Okay, so now basically the second part B, explain how the water droplets will form on glass bottle A. So just now I say why is there no water droplets on bottle B? Now why is there droplets on bottle A? Same thing. Okay, so first you need to tell me that it is warm water vapor, or you can say hot water vapor, okay, from the surroundings. Water, what's wrong with this thing? Wait, vapor from the surrounding. So you need to tell me there is a comparison, right? Outside is warm water vapor. You don't just say warm air, okay? Because air itself is not really a scientific word, right? In this case, we're talking about water cycle. We talk about water in the air, in the gaseous state, which is water vapor, yeah? So warm water vapor from the surroundings touches the cooler surface of glass bottle A. So you need to tell me it touches the cooler. Remember we talked about condensation, right? Remember always have to talk about touching the cooler surface. Always remember condensation, you cannot just say warm water vapor and then touch the surface. It must have touches the cooler surface. Remember I taught you condensation start with letter C, right? Condense, so it's cooler. Okay, so it touches the cooler surface of water A. Then what happened? Lose heat or gain heat? Okay, cooler surface of glass bottle. Actually, I would say cooler surface, cooler outer surface. Sorry, I need to be more specific also. Cooler outer surface of glass bottle A. Then what happened? Lose heat or gain heat? This is half mark. Half mark. Okay, because it's just observation. This is what your evidence is. Now the concept comes. So when it touches the cooler surface, it lose heat, right? So it loses heat. Okay, so loses heat. And then what happened? What is the change of state? So what is the process first? Loses heat and condense. Okay, condense. This is marked again because this is actually again the concept. And what is the change of state? Into what? Tiny water droplets. Now, this is the answer. So, this will give you another half mark. Now, so let me just repeat. Take a look here. So, whenever talk about condensation, you must always say it is a warm water vapor touching the cooler surface of something. Okay, so in this case, the warm water vapor touches the cooler surface of what? You need to mention. You cannot just say touches the cooler outer surface. It can be bottle A or bottle B, right? So cooler outer surface of bottle A. Then when it touches, what happened to it? Remember, lose heat or gain heat. It loses heat. Then what is the process? It condenses. Then what is the change of state? tiny water droplets. So again, always remember, whenever we talk about water cycle, you must tell me the process, which is condensation, evaporation, etc. You must tell me whether it is losing of heat or gaining of heat. Then you must also tell me the change of state. These three must be there for every water cycle question. Understood? Okay. Thank you. Okay, now let's take a look at question 43. Samantha conducted an experiment with two setup A and setup B here. Now, look at the setup. Let's take a look. There's iron ball, there's material X, material Y. Let's put side by side each other. And then we have magnet. There's an original position. And then he moved, like you can see, this arrow here, he moved the magnet here. Now, and then where's the ball? The ball is still here. Now, then after that, you look at setup B. Same thing, we have the iron ball, we have the material. Now, instead of material X and Y, okay, let me just highlight here. This is material X, and this is material Y. Here, the only difference in the setup, remember I say, always take a look at the difference in setup. Material Y and material Z. Now, when he put material Y and Z, and he moved the magnet here again towards this way, okay, this is an iron ball. So magnet and iron. Iron is a type of what? Ask yourself. So iron is a type of magnetic material, right? Magnetic material, just need to M. Okay, so now this iron ball is able to move together with the magnet. When she moves the magnet here, this iron ball also moves. So obviously you know this topic here will be on P3 magnets. Now, but what is the key concept here? That is something that you need to figure out, right? Now, so something about, hey, the magnetism, what allows this iron ball, because the iron ball will be attracted to the magnet, so definitely it will just follow the magnet, right? Wherever it goes. But now here, when I put material X and Y, it didn't move at all. So something about the magnetism that doesn't, I mean, it doesn't get through. There's no magnetism here in between that allows the magnet to attract the iron ball. Okay, what is the key concept then? We learn about something like magnetism cannot pass through. So the key concept here is magnetism cannot pass through, magnetic material, right? And of course, we can also say magnetism can pass through non-magnetic material. Okay, so this is the key concept that we are looking for here. So now let's take a look. The only difference here and this setup here and this setup here is material Y. Material Y remains the same. Am I right? Material Y here remains the same. But the only difference is material X and Z here. So this material Y, if this one, if you see material Y, this ball, even if material Y is there, it can still, iron ball can still attract the magnet. So that means these two are made up of what? Non-magnetic material. So Y and Z are confirmed non-magnetic material. However, here, even though Y is here and Y is non-magnetic, what does it tell you about X then? That it doesn't allow it to pass through. Magnetism cannot pass through. X is a magnetic material. So with that said, we can straight away say X is a magnetic material, Y and Z is non-magnetic. Clear? So it just take a look here. Magnet can attract the iron ball because magnet attract magnetic material. Iron ball is a magnetic material. So it means magnetism can pass through these two things. That means magnetism can pass through material Y and material Z that is non-magnetic. So Y and Z is non-magnetic. But in this case, even though we have non-magnetic material Y here, but the magnetism still cannot pass through because we have material X. And that would definitely mean that material X is a magnetic material. Clear? Okay, now the second part, part B, why the iron ball did not move in setup A? This is exactly what I have explained just now in part A. So why is it so? The key concept is magnetism cannot pass through non-magnetic material, right? So you can actually say at first, you can also say material X is non-magnetic, so magnetism cannot pass through it. Okay, this is the first point here. So this one will give you 1 mark. But you see here, if it's 2 marks, that means I need 2 points, right? So material X is non-magnetic material. It's a non-magnetic material, so magnetism cannot pass through it. But by saying that magnetism cannot pass through it itself, that wouldn't suffice. Because, or that's not enough. Why? Because you first need to tell me that the magnet then, therefore, the iron ball is not attracted to the magnet, because magnetism cannot pass through, iron ball is not attracted to the magnet. That is the other part. So what if the magnetism cannot pass through? So that's when you have to explain. When the magnetism cannot pass through, magnet would not attract the iron ball to move along. That's all. And that will give you 1 mark, another 1 mark. So a lot of you just tell me, oh, magnetism cannot pass through non-magnetic material X. Then you just give you 1 mark. But that doesn't tell me why it didn't move. Because magnetism cannot pass through, that means the magnet doesn't attract the iron ball and it doesn't move along. That's the main idea that I'm looking for here. Okay, so you need to be very specific in size, right? You cannot just stop there. Add a little more of your explaining, of your reasoning. Okay, you cannot just put for me a concept. You must link back to the question. That is the major point that you have to do. Okay. Okay, now question 44, which is the last question. This question is very interesting. And this is the concept that I've actually told you about it sometime back. Okay, don't remember. Don't know whether you can remember. Now, the hand dryer is used to dry wet hands. Have you seen this in your toilets? Right, the hand dryer. And what is it blowing out? It's blowing out what? Hot air. Some of you tell me, oh, it's blowing out cold air. No, but most of the time, hand dryer is to blow out hot air. Okay, you put your hands there, it's hot. Now, it's to blow out hot air and your hands are wet. So, something about hot, again, something about heat, something about wet. Now, and then something about drying off. So, that means the water droplets on your hand now is gone to become your water vapor. So, again, we are talking about the topic is P5 cycles. Okay, and the key concept here, what is it that allows your water droplets to become water vapor? Think about it. The process of evaporation. So that is the key concept here. The process of evaporation is a process of what? Gain heat or lose heat? Gain heat and change to what state to what state? Change. So let me just put water droplets to water vapor. Simple. Okay, so this is the key concept that I'm looking out for. So here is just trying to say how the hand dryer help to dry your hands. So first tell me, the hand dryer blows out what? Okay, this is your evidence. So the hand dryer blows out hot air. So you can say that. Okay, now then what will happen to your hand? The water droplets on the hands. What will happen? Here, refer here. Water droplets on the hand gains heat, right? Gains heat. What is the process? Okay, if you tell me gains heat already, I'm giving you half mark. Okay, gains heat. And what is the process? Evaporates. So you need to tell me evaporates and what? Into what? Change of state into water vapor. And this one, I will give you another half mark. Then, you can say thus, drying the hands. So this one relating it back to the question. So thus, drying the hands. Simple? Okay, so again, can you see if I just identify what's my topic and key concept, I can use this key concept to answer this question already and just relate it back to the question. That's all. And don't need to write for me essay or long story about this and that, this and that. No, go straight to the key concept. And you zoom it in that way and you will get the full marks. Okay? Okay, now last part. vultures, this type of bird, urinate on their legs. That means urine, pass urine on their leg and feet to cool themselves off on hot days. This is a true story. I mean, this is what vultures usually do. They urine on their legs and feet to cool themselves off. Now, tiny water droplets will form on their legs and feet when they urinate on them. Okay, again, what about the water? See, again, there's the word, there's a clue here, water droplets. And usually in part A and part B, right, they are testing about the same concept, same theme. So if you talk about cycle, then we also talk about cycle. Of course, in P6, you will see that they might put two concepts into one question. Like for example, it can be topics on cycles plus something else, topics on plant system, for example. Okay, so but in this case here, you see that it's only one topic that's tested here. That is P5 cycle still. Now, water droplets form on their legs when they urinate. So when they pass urine, these water droplets will form on their legs. And this gives you a big clue already. Why is it that these water droplets will cool themselves? It's something got to do with the part, just like humans, when we sweat, okay, and we cool ourselves down. How does this sweat cool ourselves down? Remember we talk about people having fever, then we put a or a damp cloth on your head, and then it helps to reduce the temperature. Same thing here. What concept is this? I've already told you this before. The concept of the water droplets evaporating to become what? Water vapor. And this is the giving you the cooling sensation. Okay, this is the exact same way when you sweat, right? For example, you are feeling hot after PE. Some of you holding on to bottles that can spray out this mist, right? This water, right? So have water droplets on your face, and then you suddenly feel, oh, so cool, so cool. Why is it so? You get this cooling sensation because the water droplets now at your face will gain heat from the surrounding air, and then it will evaporate to become water vapor. And this process of evaporation to become water vapor here is the one that gives you the cooling sensation that will reduce the body temperature. Same thing, just like how you are having fever, your mother will put cool ice packs on your forehead, right? And then what happened? All these water droplets on the forehead will gain heat from the surrounding temperature, evaporate to become water vapor, give you a cooling sensation, reduces your body temperature. Same concept. Can you see that I can test you the same concept in different situations? So you must understand the concept here. The main important thing is to understand the concept. Okay, so like I mentioned already, the key concept here is evaporation. Meaning evaporation is the process of heat gain. And heat gain, and what is the change of state? Change from water to water droplets to water vapor, right? And in this context, obviously it will give you a cooling sensation. Don't just tell me every part where evaporation, water in the puddle evaporate to become water vapor and gives a cooling sensation. There's no such thing, because the water vapor don't need, when the water droplets do not need to have on your ground, don't need to have a cooling sensation. Okay, now. Okay, so now answering the question, how urinating actually get the vulture to cool off? Okay, so first you have to tell me right here, the evidence here that there's water droplets when they urinate, right? So what happened to these water droplets? The water droplets on the legs and feet. So I'm just copying this part here. The water droplets on the leg and feet. What will happen? Here. Gain heat. And then this one will give you 1 mark. It gains heat from where? From where? Always must tell me it gain heat from where? From the surrounding air. Okay. And then what's the process? It gains heat, it processes, it evaporates to become what? Evaporate to become what? Water vapor. Water vapor. And this will give you another 1 mark, causing a cooling effect, and lose allows the vultures to cool off. allows the vouchers, maybe you can say allow the vouchers to lose heat and cool off at the same time. So because when it is becoming evaporate to become water vapor, it takes away the heat as well, right? And that's why it's losing heat, and this will give the cooling effect. This is exactly what I wanted to write. Simple, right? Can you see it's just the concept on evaporation? Can you see the 1 mark is actually coming from water droplets gaining heat, giving you 1 mark, and the other one is evaporate to become water vapor. That's another 1 mark. Even if you don't write giving a cooling effect, allow the water to lose heat, I don't mark you wrong. But that will be good because you again put your answers in the context of the question. Okay, that's all.